In this video, we'll talk about support vector machines. These are a pretty popular means of performing classification. The naming is pretty unintuitive, but we're going to build up some foundational ideas to see where it comes from. So the main idea is, can we draw lines to separate classes? In the example here, we have a data set, a training data set, and we have two predictors, x1 and x2. So for every case, which is a point, we're plotting the values of the predictors, x1 and x2, and we're also coloring every point by what class they are. So the blue points are class A, and the orange points are class B. So we can actually draw a line to separate these two classes. That's the dotted dashed line. And the formula for this line is x2 equals negative 1/3 minus 2/3 x1. This can also be rewritten as 1 plus 2x1 plus 3x2 equals 0. So this is the formula for a separating line. It's a line that perfectly separates classes A and B. So we're often in situations where there are more than two predictors. What happens in 3 dimensions? So when we have 3 predictors, we have a separating plane. And in general, a separating plane can be written with this formula: beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 equals 0. And even more generally, if we are in p dimensions, there's the notion of separating hyperplanes. Hyperplane is so named because it's beyond a plane, but in general, the formula for a separating hyperplane is the formula shown at the bottom, where there are p predictors, x1 through xp. So how do we actually use separating hyperplanes or lines to actually classify cases? So at the top, we have the formula for the separating line, x2 equals negative 1/3 minus 2/3 x1, and its rewritten form as a function equaling 0. So note that a case is above the separating line in this particular example if x2 is greater than negative 1/3 minus 2/3 x1. Again, this can be rewritten in terms of 1 plus 2x1 plus 3x2 being greater than 0. Also note that a case is below the separating line. It's of the orange class, the B class, if x2 is less than negative 1/3 minus 2/3 x1. Or equivalently, if 1 plus 2x1 plus 3x2 is less than 0. So if a case is above the line, we predict A, and if the case is below the line, we predict B. So in general, for separating hyperplanes, it's the same idea. If the formula for the separating hyperplane is beta 0 plus beta 1 x1 plus ... all the way up through beta p xp equals 0, then a point is above the separating hyperplane if that linear combination on the left is greater than 0, and a point is below the separating hyperplane if that linear combination is less than 0. So note that if we call class A as corresponding to the case where the response variable y equals 1, and we call class B as corresponding to the case where the response variable y is equal to negative 1, then a separating hyperplane has the following property. If we just multiply that linear combination by y, that whole thing on the left should be greater than 0. So we can actually make the following observation. It turns out that there are infinitely many possible separating hyperplanes. So take the example on the left. There are infinitely many possible separating lines that we could draw to separate the blue and purple cases. And a particular separating line is shown on the right. So given that, how do we actually find a unique solution? How do we find one possible separating hyperplane? The idea is to find what is called an optimal separating hyperplane. This is also called the maximal margin hyperplane, and the idea is this. We want to compute the smallest distance from every case, every point, to the hyperplane. This smallest distance happens to be the perpendicular or orthogonal distance, and we're going to call the smallest of these smallest distances the margin. Our goal is to find a hyperplane that maximizes the margin. This ends up giving a unique solution for what a good separating hyperplane should be, And the idea is the bigger the margin is, the more well separated the two classes are, and hopefully this will lead to better performance on test data. So for prediction, we use the optimal separating hyperplane in the same way as a general hyperplane. We predict class A if that linear combination is greater than 0, and we predict class B if that linear combination is less than 0. So an example of a maximal margin hyperplane is shown here. It's the solid line indicated in the center, and the dashed lines indicate the margin. So note that there are 3 cases, 3 points that are equidistant from that maximal margin hyperplane. These are called support vectors in the sense that if these cases moved, then the hyperplane would move. So in this sense, these cases, these support vectors, support where the maximal margin hyperplane is. It's only these cases that end up affecting how we draw that maximal margin hyperplane and none others. So for example, adding this purple point does not change the margin at all because it's not one of the ones that determines the smallest distance, the smallest of the smallest distances from cases to that maximal margin hyperplane. So how do we actually find the maximal margin hyperplane? It's the solution to an optimization problem, which we're going to set up here. So our data consists of n training cases. The response variables are y1 through yn for each training case. The classes are -1 and 1. There are n predictor vectors, so x1 through xn, where each x is a vector of p different predictors. So the solution to finding a maximal margin hyperplane is the optimization problem shown at the bottom. We want to find the values of beta 0, beta 1, all the way up through beta p in order to solve the optimization problem at the bottom. So this maximize m, this m is the margin. It's the minimum of those smallest distances of each point to the hyperplane. This latter constraint says that all cases must be at least m distance away from the hyperplane. And this last constraint is more of a convenience. This makes sure that the perpendicular distance from every point to the hyperplane is equal to this linear combination, as opposed to some constant multiple of this. This is just nice for interpretability. So the downside of maximal margin hyperplanes is that they're very sensitive to what exactly the training observations are. That is, they're highly variable. So the particular maximal margin hyperplane for this data set shown on the left is shown in black. But with the addition of one single blue data point, the maximal margin hyperplane shifts. It shifts from where it was for the dashed line. It is now the solid black line, so it shifts quite a lot. Another downside is, what if cases can't be perfectly separated by a hyperplane? So in the example here, there's no possible line that we can draw that'll perfectly separate the blue and purple cases. This is a downside of the maximal margin hyperplane because we assume that there is some hyperplane that can perfectly separate the two classes. So an alternate approach in which we actually purposefully find a hyperplane that doesn't perfectly classify all training cases is called a support vector classifier. So the goals are to decrease sensitivity to individual observations. We don't want the hyperplane, that separating hyperplane, moving so much with just the addition of one case. We want to classify most training cases accurately, and we hope that overall this slight amount of misclassification leads to better performance on a test set. So building the support vector classifier is an optimization problem, just like finding the maximal margin hyperplane, and there are some commonalities to that optimization problem. So in particular, the areas highlighted in pink are commonalities with building the maximal margin hyperplane. But there are some additional features that allow for this potential misclassification. We'll go over that now. So these additional epsilons are called slack variables, and these actually allow cases to be misclassified. So if we look at the constraint shown here, we see that there's this 1 minus epsilon additionally to what we had before when we built the maximal margin hyperplane. So it turns out that when an epsilon is equal to 0, case I, so each epsilon corresponds to a case, it turns out that when epsilon I is 0, case I is on the correct side of the margin. Why is that? Because when epsilon is 0, this condition ends up being the same condition that we used to ensure that every training case was at least m away from that separating hyperplane. So when epsilon is greater than 0, this quantity on the right will be less than m, and this will be the case when case I is on the wrong side of the margin. It may be on the correct side of the hyperplane, but it's not past that m distance. It's not past the margin. And finally, when epsilon I is greater than 1, then this quantity, this m times 1 minus epsilon, becomes negative. And in this case, case I is on the wrong side of the margin and on the wrong side of the hyperplane. So it's completely misclassified. Finally, we have these constraints that these slack variables, these epsilons, are non-negative, and they have to add up to a budget. So they have to overall be less than or equal to some constant c. We can think of c as some sort of budget. So let's get a little more intuition for the optimization problem with this small example. So in this training set, there are 12 cases of the blue and purple classes. The hyperplane that is estimated by the support vector classifier is this solid black line, and the margin is indicated by the dashed lines. So below the hyperplane is the purple side, and above the hyperplane is the blue side. So we're going to delve a little deeper into this top constraint of the optimization problem. So when epsilon I is 0, this is the situation where cases are on the correct side of the margin. So it happens to be that cases 2, 3, 4, 5, and 6 are on the correct side of the margin because they're at or past that dashed line. They're past the margin. It happens to be that for the purple class, 2 is directly on the margin. And similarly for the blue side, cases 7, 9, and 10 are on the correct side of the margin. That is, they're past the dashed line on the upper side. And it happens to be that case 9 is directly on the margin. So when epsilon I is greater than 0 but less than 1, these are cases where this is the situation where a case is on the correct side of the hyperplane, that solid black line, but on the wrong side of the margin. So for the purple class, this is case 1 because it is indeed below that separating hyperplane, well, the hyperplane, but it is not on the correct side of the margin. That is, it's not below the dashed line. Similarly, for the blue side, case 8 is correctly above the hyperplane, but it's not above the margin. And finally, when epsilon I is greater than 1, this is the situation where a case is completely on the wrong side of the hyperplane. So for purple, this is case 11. It's above the hyperplane when it should be below. And case 12 for blue. It's below the hyperplane when it should be above. So it turns out that cases that are directly on the margin, that dashed line, or on the wrong side are called support vectors. It's only these cases that affect where that solid line hyperplane goes. So coming back to this large optimization problem, it actually turns out that there is a bias variance trade-off for this C. The fact that the sum of these slack variables has to be less than or equal to some constant C you can imagine that there's some sort of bias variance trade-off in play here. We're going to discuss this in class. So a computational note, it turns out that solving the optimization problem for the support vector classifier only involves taking inner products of the observations rather than using the observations themselves. So let's define what an inner product is. So if I have two vectors, xa and xb, that each have p components, so this is like a p predictor situation, the inner product is defined by these angle brackets shown here, and it's defined as this summation. So this summation is not that intuitive. Let's look at an example. So xa is the vector 1, 2, 3, 4. There are 4 predictors, and xb is 2, 3, 4, 5. We compute the inner product by taking the corresponding entries of every element in the vectors. We multiply them and add them together. So the 1 and 2 get multiplied together, 2 and 3, 3 and 4, and 4 and 5. So we add up those products and we get an inner product of 40. So just as one more example, we have the two vectors 1, 2, 3, 4, and 5, 6, negative 5, negative 0.5. We again multiply the corresponding entries and we add these products together. And here we get an inner product. Dot product is another name for inner product. We get an inner product of 0. So it turns out that we can actually use inner products to write the formula for a hyperplane function. So the hyperplane function f of x can be denoted in this way, shown here, with inner products. Originally, we had denoted hyperplanes with this linear combination, this beta 0 plus beta 1 x1, etc. equals 0. It turns out that we can write the formula for hyperplane in this notation with inner products as well. So this will be useful actually when we introduce an improvement to the support vector classifier in just a moment. So there are actually limitations to the support vector classifier. It is nice in that it addresses some of the issues of extreme sensitivity to slightly different training data, but it is also limited in that we can only draw linear decision boundaries. So in particular, in the data situation shown here, the purple cases are completely in the middle between the blue cases on either ends. So we actually can't draw just one line in order to separate these two classes. In fact, the hyperplane that gets estimated in the support vector classifier is shown on the right with the solid black line, and the margin is shown with the dashed lines. So we see that this decision boundary doesn't at all separate the blue and purple classes. So what we'll need is some nonlinear transformations to help us. So this is the idea of support vector machines. So the idea is to enrich the space of predictors by using variable transformations. This is very much the same idea that we used when we talked about splines earlier when we wanted to deal with nonlinear relationships. So these transformations are achieved by something called kernel functions, which will be denoted as a function k that takes as input two vectors, x and xi. So to reiterate what was introduced earlier, it turns out that the support vector classifier can be written in this form shown here with inner products. There's just a slight modification to adapt this to express support vector machines. So instead of using the inner product in this summation here, we replace that inner product with a generalization. We replace it with kernel functions, which are these potentially nonlinear transformations of the predictors. So to make this concrete, let's look at an example. This is the same troublesome data set that we saw earlier. A support vector classifier only tried to draw a linear decision boundary and it did not do well. So two examples of kernel functions are shown here at the bottom. The polynomial kernel is on the left, and the radial kernel is on the right. These two functions define nonlinear transformations of the predictor variables, and we see, based on the pictures, that nonlinear decision boundaries actually get formed. So on the left, with the polynomial kernel, if we look between the solid lines, this nonlinear version of a separating hyperplane, we actually see that these lines actually do better separate the blue and purple classes. And similarly with the radial kernel, this nonlinear transformation also helps better separate the blue and purple classes. We see that almost all the purple points are contained within that solid black circle. So in summary, the motivating idea behind support vector machines is the maximal margin hyperplane. They're hyperplanes that perfectly separate two classes. And in order to build them, we maximize the margin, which is the smallest of the smallest distances of each case to the hyperplane. The downside of these maximal margin hyperplanes is that they're quite sensitive to new data, and it may not even be the case that classes are perfectly separable. So the support vector classifier tries to alleviate some of these concerns. It purposefully allows some cases to be misclassified. We do this with slack variables, and it turns out that the extent of misclassification can be tuned. So tuning parameter, we have to think of bias variance trade-off. We'll think about that in class. And finally, these two previous classifiers are also limited in that they only draw linear decision boundaries. Support vector machines try and improve upon that by extending the support vector classifier. We do this by having nonlinear variable transformations.